Welcome, everyone. We are officially in the last set of podcasts for this semester, which is kind of crazy considering where we started with all this in March. Anyway, a couple little side notes. Well, hopefully I have your attention. First one is to remind her about that optional project to please consider taking advantage of. It is the only way that you can add a good chunk of marks to Unit A, which of course comprises 50% of your overall marks. So it's a pretty good chunk of change in terms of being able to improve your mark significantly. Next thing is I really recommend that this week 11 assignment, you try to get it in before the actual due date. So the due date is that Monday, June, I'm going to lose sight here, 15th, right? Now, think about this though. Your final assignment is due that Friday, June 19th. And some of you are kind of slagging in terms of when you hand stuff in. So if you end up handing in this one really late and all of a sudden you have 1 day left before June 19th to hand in that final assignment, which is not going to be small, heads up, ultimately it should take you 3 hours is what it would come down to, right? So it's a big assignment. It's the whole course and it's in replacement of a final exam. So it won't be little teeny tiny. Really though, guys, you need the week to work on it. If you work on it for 40 minutes a day, 5 days in a row, you'll finish it. If you try to push through it in an hour, it's not going to go so well. So, end of the end, please try to get this one in on time in order to allow yourself to have a less stressful situation where you can ask me questions, where you can work through things, etc., etc. Let's end this year strong. Okay. We are moving on to our last topic of the course, which is crazy to say, and this is about titrations. Now, titrations, guys, factor in huge into Chem 30 as well. So it's really important that you are thinking about the different parts, that you're paying attention to the lab we do at the end of this week, and that you're being considerate of how your stoichiometry concepts can be applied into a titration process. Now, this first podcast is just going to be an introduction to what titration is. We're not going to do any calculations in the first podcast. And honestly, there's no questions in your assignment associated with the first podcast. We'll save that for the second one. So let's get right into it. Now, ultimately, this idea of titration completely builds into the stoichiometry you've already been doing. Now, ultimately, sometimes information that's been presented to you in questions, we don't just know. It had to be figured out experimentally. And ultimately, how is that done? It's done through something called a quantitative analysis. Now, I want you to consider those two things. We have a qualitative analysis and we have a quantitative analysis. When you think about what is the difference between those two words, it has everything to do with qualities versus quantities. And ultimately, anything that's a quantity is number based, whereas qualities are characteristics, color changes, looking at potentially descriptive things like, ooh, I saw bubbles of gas, etc., etc. Okay? Now again, titrations, numbers, quantitative. Now, a lot of new lingo, a lot of definitions that come into this that you're going to want to be comfortable and familiar with because they will be mentioned in questions. And if you don't know what the words mean, it's hard to apply them into a question context. First things first, the whole idea behind a titration is to determine concentrations. And ultimately, you're figuring out the concentration of one solution by observing how it reacts and writing out, of course, a balanced reaction with, and this is not a new definition, it's one we've come across before, a standard solution. And all standard solutions are, to remind you, are solutions with a concentration we know. Right? So essentially, if I said to you, I have a standard solution of 0.100 mole per liter hydrochloric acid. Oh, again, that simply means you know the concentration. Then we can use that one that we know to help determine the unknown concentration. That's the whole point of the titration. And that process of finding out the unknown one is called standardize. So if you ever sent to a lab and said, hey, standardize this solution, what I'm saying to you is, hey, react this solution with another one where we already know the concentration in order to figure out this unknown concentration. Stoichiometrically, of course, we're going to use the mole ratio to do that. And I will show you examples of this, right? It'll come up later. Now, ultimately, we assume through this process that all of the limiting reagent reacts and that it reacts according to the ratio. Now, that being said, it's not 100% perfect scenario, but it's still a really good way for us to get a fairly decent idea of what the concentration would be. All right, let's continue. This is a titration setup. Now, ideally, you would have been doing a lab with this and you would have been playing around with the lab equipment and trying to get good results, etc. I've included at the end of this assignment a demo titration that is done online that you need to follow through step by step with, of course, some different understanding and analysis questions. That's our reality with you being home with COVID with this, guys, and it's just kind of happening last minute. So do your best to understand the processes. Make sure you take the time to understand these parts and to honestly do a bit of memorization of what's what. Let's begin. So this huge long piece of glassware that's attached, I'm going to start right at the top, is called a burette. Okay, B-U-R-E-T-T-E. Again, I'm referring specifically to the piece of glassware. They're expensive. They're pricey little things because they are carefully calibrated and they're very accurate in terms of the volumes that they measure. Now this next line, which I'll just trace in yellow here, is actually referring to the liquid inside the burette. And that liquid has a special name that will be referred to quite often. It's called a titrant. And again, by definition, it is the liquid in the burette. And that's important to take note of, right? It's not referring to a piece of glassware, but it's specific to the liquid, the solution in there. All right, let's continue over here. This is a fancy clamp, and I'm going to use kind of a blue highlighter so you know where I am. This one is called the burette clamp. So it's a special clamp that is used to attach to both the retort stand, which I'll label in a moment, and to attach to that fancy piece of glassware. Speaking of which, and I'm going to a pink highlighter now, this is the retort stand. That's what I'm referring to. And essentially it's a nice stable stand that we can use to attach lab equipment in order to support it and effectively keep it from falling over. All right, I'm going to go back to a yellow highlighter. I'm down here. This is a special valve that's on the bottom of a burette, and it's called a stopcock valve. The reason for that is because it's super accurate. So we're able to very carefully turn it in order to achieve a drop by drop addition of the titrant. And that's a big deal, literally one drop at a time, the accuracy. Now, what are you trying to put one drop at a time into? Well, that's this right here. Now, yes, this is an Erlenmeyer flask. That should not be a new word to you. Erlenmeyer flask, but there's another new word that is the liquid inside. So make sure you note this, please. The liquid in this flask has a fancy name, and it's called an aliquot. Whoopsies. And it is spelled A-L-I-Q-U-O-T. Right? And that's a big one. The aliquot. There we go. Again, aliquot is the liquid inside. So if I highlight the aliquot word yellow, I would highlight this liquid in here yellow. That's what it's referring to. And there you have it, guys. Now, keep in mind, I'm going to be referring to these different items regularly in the context of notes, conversation in the podcast, questions, and you should now be familiar with it. And if you're not, have that handy dandy diagram in front of you so that you can refer back to it. Okay, let's continue. So going further with these definitions, I just mentioned to you titrant. If this is the solution in the burette and the diagram in front of you, it's the pink one, right? Then ultimately what's going to happen is we use the titrant drip by drip going out of the burette and into the Erlenmeyer flask in order to have a reaction. So you're reacting, I'm going back to this one, you're reacting the solution, which I'll color pink in here, right? There's your titrant. You're reacting this pink solution by putting it drop by drop into the yellow solution. And then we're going to mix them, right? So we can carefully control the reaction bit by bit by bit. How do you decide when the reaction is over? We'll get to that. Okay, going back to this. With a burette, you always need to record the initial volume, the starting volume. And it's really important to remember that liquids have, when they're dissolved in water, right? Well, a liquid that's an aqueous solution has a high cohesive property, which means we get a meniscus. And I wrote the word meniscus here. So I'm going to zoom in here. The meniscus is always the bottom of after it sticks to the sides. So if you can kind of imagine going across here, that's the bottom of the meniscus. And look at how it's actually numbered. If this is 3.0, then if I take a highlighter here, this is let's see, let me go thinner. This is 3.1. This is 3.2. That's not where the meniscus is. This is 3.3, right? That black line that I just highlighted yellow. So my initial volume is 3.3 milliliters. Okay, and it's been measured to the 100th on this one, 3.30. Now, after a bit has been allowed to drip out, then we get to the final one. And that's where, if you look at this one and we go close on it, again, key thing, we have to measure to the bottom of the meniscus, right? So we go down to here, and look at where this one is at. If we go all the way down, 3.1, 2, 3, 4, 5, 6, 7, 8, to the bottom of the meniscus, which is here, 3.9. So we're at that point, right? That's how we carefully measure this. If we'd been in the lab, you would be doing this, and you would have to measure those and be accurate. So now we'd be like, okay, what volume was actually released from the burette? Well, we would subtract those two. So we take one and be like, okay, we have 3.90 minus 3.30 milliliters. So the actual volume used is 0.60 mils. Oh, there we go, right? From the initial to the final. Ultimately, what's the point? Well, to figure out what amount of titrant is required to actually complete the reaction, right? Initial versus final. All right, let's continue. Another definition, the aliquot. If you remember back, I told you the aliquot, I'm going to flip over here, is the yellow one that I put into the Erlenmeyer flask. That's the aliquot. And it's a known volume. Why? Well, because you measure it. This is a tool, guys, that I have shown you before. That is a volumetric pipette, and it measures very, very specific volumes. Quite often in titrations, we will put measurements of, say, 10 milliliters into each Erlenmeyer flask, and that's what we use in the reactions. Now, I'm saying reactions plural is because you can't get this done in one trial. Usually there is a minimum of 3 trials, often 4, 5, 6, 7 trials to get the results that we want. But ultimately, that aliquot is the solution in the Erlenmeyer flask. And I'll remind you, we accurately, carefully measure the volumes of the volumetric pipette. Okay, here's another new word, equivalence point. Ooh, here we go. So equivalence point, guys, is exactly when we know the reaction is complete. And it is a super important word. It's one that will come up again and again this year and into Chem 30. And we know that the equivalence point happens when all of the titrant that we've added has completely reacted with all of the aliquot. Now the aliquot, the one that's in that Erlenmeyer flask, well, that's the limiting reagent, guys, because that's the one where everything gets reacted first, right? So once all of that is reacted by what you're adding in from the burette, then and only then do we know that the reaction is over, right? Okay, let's keep going. I keep on saying you know when the reaction is over, but I haven't actually told you yet how you know. And this is when indicators come into play. Indicators, the nature of what they are, do this wonderful thing where they change color depending on the pH. So quite often when we deal with titrations, we're dealing with acid-base titrations. And the lovely thing is that the reaction is complete at a certain pH. So we pick a good indicator in order to measure the pH correctly of when the reaction is done. Awesome. Okay, here's just a quick list on the side. There are some different pHs. Pretty common ones that we would have used if we were in class are things like phenolphthalein, bromophenol blue is really familiar, methyl orange, okay, any of those. Here's another word for you, endpoint. Now, endpoint is similar to equivalence point in that they happen at the same time. Equivalence point, though, is more about the volume added of titrant. Vice versa, though, the end point is very, very specific to the color change. So I'll say it again. Equivalence point, right? That was on this page over here. Equivalence point is about the volume of titrant added to complete the reaction. End point is about a color change, which signifies the end of the reaction. They happen at the same time, but they're referring to two different distinctive parts of the reaction being over. Alrighty, couple little side notes. That standard solution, remember standard solution is the solution where you know the concentration of it already. It could be the one in the burette, the aliquot, or the one in the Erlenmeyer flask, the aliquot, or the standard solution could be the one in the burette, the titrant, either one. Now, even though many, many titrations are possible, we are really, really focused on those acid-base titrations. This is the key, okay? All right, guys, that's the end of this first podcast. Absorb it. Make sure you can have a bit of understanding. I would highly recommend you look at the notes and add in the things from the podcast and from what I've already posted in the PDF version. And then I will see you shortly for part 2 of titrations when we get into the calculations.